Hello everyone, welcome to another session on robotics. So far we talked about some of the components of the robots including sensors, actuators, and from now on we're going to get into more theoretical side of robotics, specifically on how to mathematically model a motion of a robot. And we're going to start by talking about rigid body motion, how a rigid object can move in 3D space and how we can quantify its motion. And then we will use this to model the robots. Let's start. Previously, we talked about robots. And one thing I want to mention that in this course, we're mostly focused on robotic manipulators, a specific type of robots used to manipulate their surrounding environment and objects around them. There are other types of robot, drones, mobile robots, legged robots, humanoid robots, and we're going to talk about modeling of robotic manipulators, and all of the methods that we're going to talk about can be generalized to model those robots with small modifications, but we're focused mostly on robotic manipulators. And robotic manipulator, as we mentioned, is made of several links that are connected using joints. And the goal of modeling of a robot is to relate its configuration space to its workspace. Now let's talk about what is this configuration and workspace. Consider this robot that has four links and also three joints. Based on the length of these links and how much these joints have moved, the end effector of the robot can occupy a certain space in 3D space. And this space is called workspace, which we have shown with this hatched volume. And you look at it from top, it's this area. So if we move these by specific angles and displacement, the end effector will go somewhere in this space. This space is called workspace. And the configuration space is the space containing all possible joint inputs. For instance, for this robot, we have three joint variables, two rotations for these two joints and one displacement. This will form our configuration space, and it has a dimension of 3. It has 3 parameters. The workspace is where the end effector can be, and it usually has 6 parameters: x, y, z position of the end effector and its orientation around, let's say, x, y, z. And the goal of the modeling is to find a function that gives us the workspace as a function of the configuration space. Before we begin, we need to uh, define some terms for rigid body motion that we're going to use a lot in modeling of the robot. What is rigid body motion and how can we quantify this motion? First, let's talk about rigid object. A rigid object is an object that cannot deform, like this triangle in these images. If we want to give a mathematical description of rigid object, a rigid object is an object that if you select two arbitrary points on it, the distance between these 2 points never changes no matter how this object moves. This is a rigid object, it never deforms. Now, when this object moves in 3D space, it can have two different types of motion or a combination of these two. One is translation, linear motion, and one is a rotation. And the goal of this session is to quantify these two types of motion, and then we can use this to model robots. How can we quantify translation? If you think about it, you can probably guess that we're going to use reference frames and vectors. We can always define a frame for this 2D case called XY frame. And then the position of the object before it moves, let's say it's given by vector A, it moves by this vector, let's call it B, then its new position is given by a vector called C, and it's easy to understand that the new position of the object is actually equal to its old position plus how much it has moved. This way we can actually quantify the motion of that object. And if we write this equation for any point for the object, because it's rigid, we can also write it for the other points, which is only, let's say, at distance of d. All we have to do is add d to all these vectors. And one thing that you have to keep in mind is when you want to use reference frames to write down the motions of a rigid object, your reference frame should be an inertial frame. What does it mean? Inertial frame is a frame that's either fixed, stationary, or it's moving at a constant velocity. A reference frame is a frame where laws of Newton exist in it. If the frame that you picked, the red frame here, is moving by non-constant velocity, then this equation, this summation of vectors, is not correct. So always we need a fixed frame. And one thing to note that if we call this frame A, all the vectors must have been written with respect to this frame. So at the vector C is defined in frame A, vector A is defined in this frame, vector B is also defined in this frame. And we show that using this small superscript. So translation is straightforward. How about rotation? How can we quantify rotation? That would be a bit more complicated, and we're going to talk about it in this session. Before we can quantify it, we need some ground rules for defining reference frame. As I said, reference frame has to be stationary, inertial frame. And we also need to use right-hand rule to define the reference frame. What does it mean? If you want to define a frame, these three axes of the frame should follow these rules. If one of the axes is alongside your index finger, the second one is alongside your thumb, the third one should follow this finger. And why do we need this right hand frame? Because we want all of us to write equations in one specific frame. If I use this frame and let's say someone else uses a frame that's not right hand frame and its third axis is like this, our equations won't be the same. It won't make any sense. So we all need to use one type of frame, and we use right hand frame. Another way to define right hand frame is using your right hand like this. Assume one axis is alongside your fingers. The second axis comes from your palm, comes outside of your palm. Then if you rotate from one axis to another axis, your third axis is your thumb. So 1, 2, 3. This is how we define frames. Now that we define frames, how can we represent rotation or orientation of an object in 3D? Consider this very simple case. When we have a frame called frame A, it is our base frame, and this frame has rotated now to form frame B. How can we quantify this rotation, the orientation of the new frame B with respect to frame A? For translation, we show that we do it simply using summation of vectors. But how about rotation? Let's do it now together. We have our initial frame A and we have a rotated frame B. And we want to write the coordinates of the rotated frame with respect to the initial frame. One thing on the side, we need to define projection of each of these vectors showing the axes of the rotated frame with respect to initial frame. Remember that we have projection of a vector defined as norm of that vector length of it times cosine of theta, the angle between these two. This is called projection. Also, we have dot product of two vectors is equal to transpose of one times the other one, and it's equal to length of these vectors multiplied by cosine of theta, the angles between these two vectors. From this, we can find projection as the dot product divided by length of vector B. Now to find the projection on vector B, we multiplying this by B, by the normalized vector B. This would be projection of A on B. Now let's use this to write the rotated coordinate frame B with respect to the initial frame A, writing principal axis of the red one in respect to green one. First, the x prime. It has a projection along x. Using the same formula, it is x prime times x projected on x divided by length of x squared. X is a unitary vector, principal axes are unitary, so its magnitude is 1. Similarly, it has a projection on y and z. You can write this for the y prime axis and z prime as well. Now if you look at this, we're able to write this in a matrix multiplication format as well. All we have to do is gather these terms. This is an equation but written in matrix format. And now you can see that this whole transformation, writing the rotated frame with respect to initial frame, can be written in a matrix format. And this matrix is usually called R, meaning rotation. Using this, we can bring the frames of the initial frame into the rotated frame. All we have to do is multiply the vectors that we have in this frame by this matrix, and it will come to that frame. Now we can do this for the different way as well. For now, I written the coordinate frame x prime, y prime, z prime, the rotated one, as a function of the initial frame, green one. We can write the green frame coordinates in red for coordinate frame as well, with respect to the red coordinate frame as well. Let's quickly do that too. For instance, we can find projection of x along x, y, z prime. the first element would be, for instance, x transpose x prime times x prime. Similarly for y and z. We can do this for y and z axes as well. Now looking at this equation, we can write this as a matrix multiplication. This is also a rotation matrix. Now if you look at these equations closely, you would see that the first one will bring components in frame x, y, z into frame x prime, y prime, z prime. The second one does exact opposite thing, brings x prime, y prime, z prime coordinates into x, y, z. To differentiate these, we use these subscripts to show each rotation matrix does what. For instance, a rotation matrix that brings xy prime frame into xyz frame, frame A, is shown using this. This means that it will bring frame B to A. So if it's multiplied by a vector, let's call this A, that it's defined in frame B, it will bring it into frame A. The opposite, the top one, it will bring frame A to B. So if it's multiplied by a vector that is in frame A, it will bring it into frame B. And another thing to notice that these two rotation matrices from frame A to B and B to A are exact transpose of each other. So if you take transpose of the first one, you will get the second one. This is one of the interesting features of rotation matrix. If you take transpose of the first one, you get the second one. To recap, we showed that orientation of a frame with respect to another frame can be defined using a rotation matrix, and it is essentially projection of all of the axes of the frame inside the initial frame. We studied the example where we had two frames, A and B. A was fixed, B was rotated. We showed that we can find a rotation matrix that brings frame A to B or B to A, both of them, and they are transpose of each other. Usually in practice, the one that we really care about is the second one, something that would bring a rotated frame B to a fixed frame A, this one. If we call our rotated frame B, it would bring it to frame A. And in some textbooks, instead of x prime transpose x, you would see x transpose x prime. These are essentially the same, similar for here. This is how we can write dot product. X transpose x prime or x prime transpose x are the same. This is just one scalar number. So as we saw, we can define or quantify rotation from rotated frame to original frame using this matrix, usually denoted by R as rotation matrix. You can see this matrix has 9 elements. But the fact is that when we want to quantify rotation in 3D, similar to translation, we only need 3 parameters. And what I'm going to show is that although a rotation matrix has 9 elements, but only needs 3 parameters to be fully defined. How? Basically, we have 3 types of rotations. Rotation around z-axis, rotation around y-axis, rotation around x-axis. And any of these rotation is defined using a elementary rotation matrix. This is for z, y, and x. And the fact is, any rotation matrix in 3D is a combination of 1, 2, or 3 of these. It's a combination of rotation around Z, Y, or X. That's why we need only 3 parameters to quantify rotation in 3D and write a rotation matrix. If we know rotations about Z, Y, and X, what is the angle for them, we can write the rotation matrix as by combining these 3 elementary rotation matrices. Now, how did they calculate these elementary rotation matrices? It's very straightforward. Actually, using the equation that we already had derived, we can calculate these. I'm going to try to quickly calculate rotation around Z for you, and you can try to do it for Y and X later at home. Consider a simple rotation only around Z axis. We have one frame here, and it's a right hand side frame. If this is my X, if this is my Y, my Z would be this. Try it at home using the right hand rule. Now, if I rotate it around Z, let's call it by angle of theta. How would this new frame look like? Its Z axis would remain the same. Its X and Y axis, so it will be tilted by an angle of theta. Now, using the previous equation that we derived, rotation matrix was given by using this matrix. Now look at this figure. What is x prime transpose x? X prime times x, or x prime dot x. These are unitary vectors, and dot product of x prime and x would be size of length of x prime times length of x, which are both 1, times cosine of the angle between them, cosine of theta. What would be x prime dot y? Cosine of the angle between them, which is actually equal to sine of theta. X prime and dot z, these two are perpendicular, so their dot product is 0. Y prime dot x, y prime dot x would be the cosinus of, would be cosine of the angle between them, right? Which is actually equal to negative sine of theta. Y prime dot y, cosine of the angle between them. This is our z, z prime dot z, the angle between them is 0, so it will be 1. So actually this is the rotation matrix, elementary rotation matrix for rotation around z. We can calculate this for rotation around x and y as well, and you could see that we derive these equations. This was for z, you can similarly calculate them for y and x. There's also another way to calculate rotation matrix that I want to briefly show you. It gives you an insight into the another features of rotation matrix. Consider a similar case when we have one rotation around z-axis. And assume we have the position of this specific point that is shown by a vector, let's call it A. The rotation matrix not only shows the projection of a rotated matrix in its previous position, but it can also be used to show how much a vector denoting a specific point in 3D rotates. Consider this point that's shown by vector A. In the new rotated frame, it has a component called AX, and it has a component along Y as well, shown by AY. So that vector in the rotated green frame, A in the green frame, let's call it frame B, is defined by AX, AY, and its Z is 0. Now let's see what is A in the original not rotated frame, frame A. The A component, the X component of A in frame A, what is it? It is AX times cosine of theta, right? And also AY times sine of theta minus AY times sine of theta. What is its components along in Y direction? It is AX alongside Y. It is this one. It's AX times sine of theta. And also AY projection along Y is AY times cosine of theta. Z component is 0. Now, if we want to find rotation matrix using these green and red equations, you can actually see that A vector in frame A is equal to AX, AY, and AZ in frame A, which is equal to cosine of theta minus sine of theta times the vector in frame B. We got the same equation. So as you can see, rotation matrix not also shows the orientation of a rotated frame, but it also shows rotation of a vector in the rotated frame with respect to its initial frame. And for an elementary rotation around Z, it's defined by this matrix. If we had a rotation around Y, it would be this matrix. If we had rotation around X, it would be this matrix. And any 3D rotation generally in 3D is defined using a multiplication of these three elementary rotation matrices. And finally, recap rotation matrix, a matrix that brings one frame to another one. There are two ways to look at the rotation matrix. We usually use this superscript and subscript to define what a rotation matrix does. A rotation matrix that's written like this means that it is defining three principal vectors of frame A with respect to frame B that is rotated. If this is our frame A and this is our frame B, if we write principal axis of frame A into B, we calculate this as we did in a few slides ago. What does this do for us? It will bring any vector in frame B to a vector in frame A. This notation helps us follow multiplications. So if this matrix is multiplied by a vector that's written in frame B, it will come to frame A. If you multiply by a vector that's in frame A, it doesn't do anything. It will give you something that's meaningless. Features of rotation matrix that are interested I wanted to talk about is that rotation matrix is orthogonal and its transpose is equal to its inverse. So if we have a rotation matrix that brings a vector in frame B to frame A, its inverse is equal to its transpose, which means it is a matrix that brings a vector in frame A to frame B. This is a very interesting feature. So if you have a rotation matrix that brings a vector in frame B into A, if you take transpose of that, it will take a vector from frame A to frame B. Another feature is that determinant of a rotation matrix is always 1. And finally, a rotation matrix can be defined fully using 3 variables. And as I showed, any rotation matrix is a combination of a rotation around X, a rotation around Y, a rotation around Z axis. That's what we're going to talk about in more details in the next video lecture.